In this final video on the gas laws chapter, we're going to look at kinetic molecular theory and then why we have deviations from the behavior predicted by the ideal gas law. Kinetic molecular theory is the basic theory behind the ideal gas law. It's based on 5 principles. First, kinetic molecular theory, we're making the assumption that gases consist of tiny particles, atoms and molecules that are very, very small. This is a very true assumption that we are making. 2, these particles are so small compared to the distance between them that the volume of the individual particles can be considered to be negligible or zero when compared to the distance between them. 3, the particles are in constant random motion colliding with the walls of the container, and these collisions cause the pressure that's exerted by the gas. 4, the particles are assumed not to attract or repel each other because they are moving so quickly and so far apart that they do not have any interaction of that type, and that the average kinetic energy of the gas particles is directly proportional to the Kelvin temperature of the gas. So these are the basic principles we're using when we use the ideal gas law. Now, all of these principles are not true in all cases. We know that particles actually do have volume, and that if they do start to get close together, you can no longer consider it to be zero. We know that if particles are moving slower, that they will attract or repel. If they're held closer together, they will attract or repel. So some of these parts of this theory start to fall apart, and that's why we don't see perfect ideal gas behavior in all cases. Now, if we switch back and look at the cases that we have dealt with, the areas where we see the biggest trouble with the ideal gas law is the fact that real gases do indeed have volume, that as they cool or are at high pressure, they're attracted to one another or repelled from one another, which can cause gases to liquefy or form solids. Once they liquefy or form solids, the volume becomes constant and it no longer behaves like an ideal gas because it no longer is in the gas state. So we go back to this Charles law diagram that we did during the early part of this chapter. And redraw. You notice a number of these things are dashed lines. Well, the reason it's a dashed line, let's start with H2O, the most straightforward case that you all know something about. H2O is a gas above 100 degrees Celsius. Once it reaches 100 degrees Celsius, though, it will form a solid, and you'll see this drop and then become a straight line. It will become a straight line until it reaches 0 degrees Celsius, at which point it will actually rise and be at a higher level the rest of the way, because we actually have in water, volume is larger for a solid than it is for a liquid. For many of these others, if you had a typical curve, when it went from solid to liquid, it would drop, and then when it went from liquid to solid, it would drop again. But it would become flat after those points because at those points it's no longer a gas. So most gases at room temperature and 1 atmosphere of pressure behave as if they're ideal gases. So in most of our general cases, when we have gases, now this does not apply for water because water at room temperature is a liquid, but most gases will behave as ideal at normal temperatures and pressures. Cases where we see the biggest deviation from what we predict from the ideal gas law are cases of low temperature, where things start to liquefy or form solid, or cases of very high pressure where the particles are forced together and therefore also can be attracted to one another and form solids and liquids. In the next chapter, we're going to spend a lot of time talking about solids and liquids after we go through a chapter on energy, but we want to understand that the ideal gas law works great in all cases where something is a gas, especially cases of high temperature and low pressure. If you get to high pressure and low temperature, things start to no longer behave as a gas, they form solids and liquids, and you lose the ideal gas law properties.